I'm gonna go ahead and be asking questions, so if you guys could please answer them through the microphone, because it's a little bit hard for me to read the chat right now. But going over the first equation that's given to you, what does this stand for? The U.
The speed of the wave.
The speed of the wave, exactly, right? So speed of wave. What about lambda? What does lambda stand for?
Length.
Length. Wavelength, right? And what given units?
Meters, no?
Sources?
Sorry?
Is it a meter?
Meters, right? When you're working with a question, you always have to convert wavelength to meters in order for the rest of the units to cancel out, right? What about frequency? Oh,
Frequency.
I already said it, right? So nu, yeah, the nu is going to represent frequency. And what units?
Hertz.
Hertz, exactly. What does hertz equal to? Another term for hertz.
1/s.
1/seconds, right? Inverse seconds, exactly. So can you guys give me an example of what scenario could we use this formula for?
Do you mean like a sample problem?
Yeah. So what type of waves can you use this formula for? Better said.
Oh, light waves?
Light waves. Okay. What else?
Just radio waves.
Radio waves. Okay. So there's a certain type of well, for this specific formula, you can only use it when you're working with non-electromagnetic waves, right? Or also known as mechanical waves. Example of mechanical waves can be like sound or water waves. So that you could use this formula for sound, right? And then in the case that you're working with electromagnetic waves in a vacuum, then you can still when you're not working in a vacuum, I'm sorry. So like light going through water, and they're trying to tell you, they're telling you to find the speed of the wave, then you could use this formula, because even though you are working with an electromagnetic wave, you're working it with an when you're not in a vacuum, right? So can anybody tell me the formula that you use to find the that you use when you're working with a wavelength that's in a vacuum and it's an electromagnetic wave?
Hint, it's very similar.
It's the same thing, just with instead of U is a C.
Exactly, right? So what does C stand for in this case?
Speed of light.
Speed of light.
Speed of light. Can anybody tell me the units of speed of light?
3.0
meters per second.
Oh,
3.
To the 8th
power.
To the 8th power meters per second, right? I did hear that. So again, lambda is going to be again wavelength in meters, right? And frequency in hertz, which is equal to 1/seconds. So again, this formula you use it when you're working with electromagnetic waves that are not that are working in a vacuum, right? So let's see. Let me go ahead and give you guys an example. Okay, so let's say you're working with a wave. Let's see.
Are you gonna do a practice problem, please?
Yeah, Do you guys have any?
Before you do that, can I cut in real quick?
Mhm.
Can you give me a new page on the whiteboard, please?
Yes.
Let me annotate. Thanks, you the bestest. Okay, let's go over the visible light spectrum just because we can. Just in case they test you guys on it, just so you're a little bit familiar. Okay, so the visible light spectrum, does anybody know it by chance, by memory?
Do you mean like the colors in order or?
Yeah, the colors in order.
Oh yeah, it's red and then orange, yellow, green, blue, indigo, and violet.
Yellow, green, blue, indigo, and violet. Yes, and this is for the visible light spectrum, right? This is visible light. So because there's other types of waves, right? Because after violet, there's ultraviolet or UV, that's the stuff that comes from the sun, right? And then on top of red, we have IR or infrared. You'll deal with that later if you're going to study chemistry. Can anybody tell me which way the energy increases in these waves?
Violet, from red to
Towards
violet.
the ultraviolet, yeah.
Towards the violet. Okay, this is energy, right? In which way does the wavelength increase?
From violet to red, I think.
Yeah, the opposite direction, right? This is wavelength. So do you guys remember, there's this really fun joke, my favorite joke, to be honest. What's new?
Oh, L over that one week. Where's that?
What was that?
L over C, I think, or something like that. I don't remember.
It's the other way. It's C over lambda.
Yeah, there you go.
Right? So mu is we said C is the speed of the light, right? Lambda is the wavelength. What was nu? Anybody remember? What does the nu stand for?
Isn't it frequency?
Yeah, it's frequency, right? And then we haven't gone there quite yet, but there's another formula, right? That deals with the energy of the wave, and we use nu in there, right? And so nu turns into, not really, but well, it does turn into a fraction because this C stays constant, right? What's the value of C?
3.08. I guess 3.0 to 10 to the 10th power or 8 power.
10 to the 8th, right? And usually you'll see it with 3 sig figs, but it doesn't really matter. The 3 is the part that matters, right? So yes, so this C stays constant. So as this wavelength increases, this fraction is either going to get really big or really small, and that's going to affect the energy. So the bigger your wavelength is, the smaller the fraction, and the smaller your energy will be. Does that make sense?
Yes.
Awesome.
Yeah.
And then I don't know, can somebody look up the color ranges for the light? I don't know by memory, but it's a good idea to kind of have an idea. You won't really work with it though. I don't think so. I don't think the professors test this. Do you guys know?
I don't think they'll put specific like wavelength like numbers from the spectrum.
Okay. Yeah.
I think they'll just give example numbers and then plug them into the equation and that's it.
Okay. Yeah. But I mean, it's a good idea to kind of have, so but you probably won't need it for the exam.
I think the workbook had a problem in there where you had to identify whether the light was yellow, green, or red. So yeah, I was wondering if you needed to memorize it.
No, as long as your professor didn't talk about it during lecture, you should be fine.
Okay.
Okay, thank you.
Awesome. All right, Luis, back to you. Sorry.
Okay. No, don't worry. So going off of what Sophia said, there's another equation that we use to calculate the energy of a wave, right? Does anybody recall that that formula?
Which one?
Or does anybody remember that formula? Hint, it starts with energy, right? Energy equals to what?
Oh,
The one with
Planck's
Planck's constant.
It's
Planck's constant, exactly, times
B.
times frequency, right? Exactly. What does Planck's, what does, well, H stands for the Planck's constant, right? Does anybody remember the constant?
6.63 times 10 to the third negative 34
What about the units?
joules per second.
Joules per second, okay, and this makes sense. So what's going off of what Sophia was saying, frequency, majority of the times when you're trying to calculate energy, they're going to tell you find the energy of a wave that has a wavelength of, let's say 3 times 10 to the 3 picometer, no. Let's say, yeah, let's say 3 picometers, right? Or something like that. 300 picometers, better said. So you see that that they're giving you wavelength, right? Instead of frequency, and you know that frequency or nu is equal to
What's new, guys?
C over lambda.
The
C
speed of
over
light.
lambda, exactly, right? So you see how she told you this frequency was going to turn into a fraction. Well, those are the scenarios that frequency is going to turn into a fraction, right? Again, when they're telling you to calculate the wavelength, the energy out of a wavelength, right? So this equation is going to turn to a speed of light over lambda times Planck constant to it equals energy, right? So
I have a question real quick.
mhm.
I was just wondering, are we always supposed to convert to meters just to be safe if we're given like
Yes.
a smaller unit?
Yes, because
Yeah.
here, when you're
Here's-
working with, I'm sorry.
No, sorry, Lisa. The Planck's constant is not joules per second, but it's joule seconds, like joules times seconds.
Oh,
Mhm.
joules times seconds, right? Okay.
Yeah, because when you mathematically work it out, you would even, depending on what you're looking for, you would cancel one out with the other.
Exactly, right? So yeah, when you forget the units, you can always work it out mathematically, as Alan said, right? So it makes sense that you get those units, right? Because speed of light, the units are meters over seconds, right? And lambda, or wavelength, is going to be meters. So the meters cancel out, and the Planck's constant is going to be in joules per second. So joules per second times 1 over second, it always cancels out, right? The seconds. So you're going to be left with energy that's in joules. So does anybody have any questions with how to get the variables, the units?
Doing good.
Okay. So again, repeating what Sophia said, when you have a smaller wavelength, the energy is going to be bigger, right? Why?
Can you repeat it?
When you have a smaller wavelength, the energy is going to be bigger, right? Why?
Because of the denominator, I think. Basically, you
sorry?
divided by a smaller number. So the answer should be bigger, I think.
Well, the energy is going to be bigger, right? Think about producing a wavelength. It's going to take more energy to produce a smaller wavelength that's repeated many times than producing a wavelength that's like big and doesn't repeat itself that many times, right? So it also has to do a lot with frequency, or speed of light over lambda, right? So does anybody have any questions with this formula? Yes, no, maybe.
No.
Take the awkward silence as a no.
Okay, so moving on, there's another equation that also tells you energy, but this case it's going to be the energy released in photons, right? So Rydberg's equation, energy is equal to RH 1 over n I squared, squared, minus 1 over n f squared. What does RH stand for?
Rydberg's constant. Or
Rydberg's constant, right? Does anybody remember the constant?
2.18
It's 2.18
times 10 to the negative 18.
times 10 to the negative 18 joules, right? Okay, so what does N stand for? Think about the use of this equation.
It's the energy level.
it's going to be the energy levels, right? In this case, it's going to be the initial energy level. And NF is going to be the final energy level, right? So going back to the use of this formula, you see how I mentioned it used to calculate the energy of a photon. What is a photon?
A light particle.
A light particle, right? So does anybody know how it's produced? So you see how an electron, when it gets excited, it jumps to a higher energy level, right? And that same electron eventually has to go down. Okay, wait, it's because I see the chat, but
It's just
cannot open it.
Jeremiah.
Okay, okay.
Yeah.
So when that electron goes down, well, it has to relax some way, right? The energy that it had is it has to go somewhere, right? So that when that same electron goes down, a photon is going to be produced, right? So that's why you use the energy levels to produce the energy and to calculate the energy, right? From the energy shell that the electron jumped to its original energy shell, okay? So does anybody have any questions?
Can I cut in real quick?
Mm-hmm.
Sorry. Okay. For all my visual peeps out there, what does an atom look like? Is it just like a square or like what does it look like?
I mean, we always use a circle for it, so I'm guessing a circle.
Okay. But what about it? Like, do we have everything just like in a basket or like what's the structure of an atom?
Well, dark circle in the center, then it goes into little rings.
Yeah, what's the center called?
The nucleus or something.
The nucleus, right? And then that has
Protons and neutrons.
there's protons and neutrons, right? And then around the nucleus, what do we have?
Some rings that are
Rings
the
of what?
neutrons. I mean electrons.
Yeah, they have electrons, right?
It goes to 2
So let's
and A, then
pretend.
some other key.
Yeah, it has. I'm gonna simplify it because we're living our best life. It's Saturday morning. We don't need complications. Let's say that we have an electron right here in this middle shell. That's not how it works, by the way. Usually you excite the outermost electrons, but this is just for visual purposes. If we want to excite this electron and we want to move it an energy level, is it going to be easier to move it up an energy level or down an energy level?
Up.
Up? Why?
Well, you're exciting it. You're giving it more energy instead of decreasing the energy.
Okay.
That's how I see it. I don't know.
Is it easier to go up the stairs or down the stairs?
Down.
Down the stairs, right? So when you get excited, are you going to run up the stairs or down the stairs?
Down.
Up.
Down the stairs. It's down the stairs. Okay. Yes, you do excite your electrons. They do move around, but even if you excite it as much as you possibly can, it's never going to have really enough energy to move up an energy level because that takes way too much work. They're not going to do that. They're always going to move down or actually, okay, when we produce a photon, we're always going to move down an energy level because a photon is produced whenever an electron goes down an energy level. So specifically to produce a photon, you're always going to go from a higher energy level to a lower energy level. So when this electron, what was that? I'm sorry.
I'm sorry. Is that farther away from the nucleus?
Closer to the nucleus.
Oh, closer. Okay, I'm sorry.
Yes. So the energy levels increase this way.
Honestly.
Energy increases out away from the
Wait.
nucleus.
Sophia, can I jump in here?
Yeah, go for it.
So what she's trying to say is that when it's excited, it gets further away from the nucleus by going up an energy level. When it's like no longer being excited, it's releasing energy to make a photon, going closer to the nucleus, going down an energy level.
All right, I get you now. Okay.
Sorry for the confusion, but yes.
I'm still a little confused.
What are you confused about?
Could you just repeat that please, with the going up and down energy levels?
I got you. All right. So like when it's excited, it goes up an energy level or away from the nucleus. When it is releasing energy, it is coming back down an energy level or to it, and then or towards the nucleus. and then from there it releases a photon.
Because remember,
gosh.
energy is not created or destroyed, right? So you excited, it has energy. It goes up in
There we
energy
go.
level. When it's done being excited, it wants to go back home, right? It's done partying. It goes back to its original energy level. It has all this leftover energy. So the way that it like balances itself out is it lets go of that energy through a photon. Does that make sense?
Yes. Gotcha. Thank you.
Sorry, Luis, all yours.
No, don't worry. So does anybody have any other questions?
If anything, to just clarify, when it's an initial, it will be the excited electron, and then final is when it releases a photon, I'm guessing.
Exactly. So remember, it's gonna when you're calculating the energy, it's always gonna be from the higher energy level to the lower energy level.
And I
Well,
have yet to see a
I-
problem where it doesn't tell you Ni equals this and NF equals this. So you should be okay.
Yeah, it will normally say that, but there are some equations where it's not asking, because like sometimes a photon's not being formed, it's being absorbed. So all you need to do is make sure that you know which is the initial and where it's going to, and you should be fine.
Okay. Okay, so let's go ahead and work with a problem. So does anybody have any other questions before we jump into the practice problem?
Do
Okay,
you need one, Luis,
so
or are you good?
okay, so easy. The wavelength of the light emitted by a sodium lamp is 5 times 10 to the negative 7 meters. So wavelength, right? Given that the speed of light is 3 times 10 to the 8 meters per second, calculate the frequency of that wavelength. So how are you going to start this problem? Or how would you normally start it? Let's say in the case that the problem didn't give you the wavelength already converted to meters, let's say it gave it to you as 500 nanometers. So how would you start that problem now?
Convert to meters.
Convert to meters, right? Remember that you always have to convert to meters. Frequency, it's always going to be 1/seconds or hertz, right? So in order to cancel out the meters that are present in speed of light, you have to convert the wavelength into meters, right? So if you convert to meters, how are you going to convert to meters? So you have 500 nanometers, right? What steps are you going to take in order to end up with meters?
Is nanometers smaller or bigger than meters?
Way smaller.
Way
It
smaller,
should be
right?
1 times 10 to the negative 9 at the bottom. I
1
think
times 10 to the negative 9.
equals 1 meter. Then you just divide.
Okay, so and then meters in the top. So again, what is bigger, a nanometer or a meter?
Meter.
Right? So if you're going from something big to something small, it doesn't make sense that your exponent will be negative, right? Because again, you're going from something big to something small, or you're breaking that something big into small pieces.
Well, I'm saying negative 9 because I believe it happens to a lot of us, and it's calculators are weird.
Yeah.
And that's the
So
way you have to plug it in.
You can
Okay.
use that to the negative 9 if you say there are 1 times 10 to the negative 9 meters in 1 nanometer. But if you're going to put the times 10 to the 9 in the denominator, you have to use a positive exponent because you're going from, you're saying that there are 1 times 10 to the 9 nanometers in 1 meter because you're counting how many small things fit in the big container, if that makes sense.
Okay, so if you multiply 500 times 1 times 10 to the negative 9, what should you get?
times 10 to the negative.
5 times 10 to the negative 7, right? So now that you have your wavelength and the desired units, what are you going to do?
Plug in the values into the.
You're going to start plugging in the values, right? So what is the equation that you're going to use?
C equals a wavelength times
Frequency, right? So do you remember what Sophia told you that what's new?
C over lambda.
C over lambda, right? So in this case, you're trying to solve for frequency or you're trying to solve for new. So if you already have like it's not an acronym, but like a little saying that reminds you what frequency is equal to, you're gonna go ahead and use that saying, right? So again, what's new?
C over lambda.
C over lambda, right? So you're gonna go ahead and plug in the values like that. So what does C equal to?
Like,
It's gonna be the speed of light, or 3 times 10 to the 8 meters per second, right? What does lambda equal to? Or the lambda that we have?
5 times 10 to the negative 7.
5 times 10 to the negative 7 meters, right? So if you divide those two numbers, what should you get?
Six times 10 to the 14.
6 times 10 to the 14. Okay. Hertz, right? Okay, so does that make sense? Yes or no?
I mean, it makes sense. It's just I always struggle doing the calculator thing because
Okay, so
I played in the same way you have it there, and I got 6. So
If you plug
basically
it
they
in
cancel out.
the way that you see it here, you have to use parentheses. If you do not use parentheses, you will not get the right answer. If you plug it in as times 10 to the whatever, you have to use parentheses. If you use
plug it in
the exponent number, then you're fine. You don't have, well, I use parentheses anyway, but you don't need to.
So just plug it in like this, directly like this. So if your calculator is kind of messy or kind of like not working for you, just go ahead and apply the algebra rules that they taught you in 7th grade, right? So when you're subtracting exponents, what do? Oh, when you're dividing exponents,
You subtract them?
you subtract them, right? So 8 minus negative 7, what should that, it's the same thing as 8 plus 7, right? So what is 8 plus 7?
14.
15, right? So if you divide 3 times 5, 3 by 5, what are you gonna get?
Well, like 0.6.
I'm sorry?
0.6, I think.
0.6?
Yeah, 0.6.
Okay, times 10 to the 15. But you see how this is not the correct form of scientific notation. In scientific notation, you always have to have a number in front of the decimal. Okay, so if you move the decimal one space to the left, to the right, I'm sorry, you're gonna, what should your new exponent be?
To the 14.
To the 14, right? So this answer does make sense. So that's just in case that your calculator is not working, okay? So does everybody understand how we got that answer and how we got the units?
Does everyone understand why we moved over the exponent? Why we moved from 15 to 14 in the exponent?
Yeah.
Okay, so do we have time for one more, or do we have to move on?
Yeah, we can do one more.
Okay, so working with Rydberg's equation. Let's say you're working with an electron that got excited and jumped to the energy level to the 5th energy level. So calculate the energy emitted by by a sodium electron that is initially in the 5th energy level and went back to its original 4th energy level.
Well, for this one, it's gonna be E equals the, what is it? Rayburn constant, which is 2.18 times 10 to the negative 18. Then parentheses 1 over 5 square. Then minus 1 divided by 4 square.
4 square, right? So if you do that
Then you
in
solve.
your calculator with parentheses, what are you gonna get? Any guesses?
Remember
negative.
Panda's got.
Yeah, I don't know.
Go for it. What did you get?
I got a negative, so I already know it's, I'm not sure.
Okay.
Can
So
energy
what's
be
your answer?
negative?
Can you repeat that, please?
No, just asking them if energy can be negative. Can we have negative energy?
I don't know.
It would be
Okay.
So if the energy is being emitted by the electron, does it make sense for your energy to be negative?
I guess.
Yes, right? Again, you're releasing energy into your surroundings, right? Rather than you gaining energy. When you're gaining energy, the energy is going to be positive. Positive when gaining. When you're giving energy to your surroundings, then the energy is going to be negative, right? Because again, the atom itself is losing that energy because it's giving it to its surroundings. So when it's negative, it's when you're giving or emitting. So does anybody have any questions with why your energy is allowed to be negative in this case and or should be negative in this case?
So what's the answer? Because I don't know if I got it right anyways.
So let me go ahead and plug in my
What did you get? I
calculator
plugged it
real quick.
in.
And I got negative 4.9.
No más?
Well, to the 20.
To the 20? Positive 20?
Negative 20.
Yeah, that's what I got.
Okay, so the answer should have been e to the, can you repeat that please?
Yeah. Negative 4.9 times 10 to the negative 20.
And 10 to the negative 20 joules,
Yeah.
right?
So
So
in this
And
case, if it was, let's say backwards, which no, it can't be backwards. Never mind.
I mean, it
Hmm.
could be backwards, but it wouldn't be releasing a photon, right? Because we said that the photon is released when we go from a higher energy level to a lower energy level.
So is it possible?
Not really, because we're
Mm-mm.
measuring the energy of one photon, right? That's being released.
Yeah.
And so if we can only release a photon when we're going from a higher energy level to a lower energy level, if we go backwards, are we releasing a photon?
Me.
No, right? So no, it's not possible. They might do you whack and make you do the math anyway, but theoretically, it's not possible.
So does anybody have any questions with module 10?
I just have one question for
Mhm.
all y'all out there for this number. Is this a really big number or a really small number, and why?
So this is a really small number, right? Because if it's, remember that if your exponent is negative, then you're going to move the decimal to the left, right? If I'm not mistaken. So if you're moving your decimal to the left 20 places, then your number is going to be like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, until you reach the 20th zero for 49 negative.
Yeah.
Don't worry, we got it. Like we already knew.
I meant-
Like it was a small number.
I was asking the students, but thanks.
I have one last question.
Oh, it was
Yeah.
for the question. Oh. Oh, I'm so sorry.
I just wanted to ask, some of the problems it uses kilojoules per moles for the energy given. Is there any
Yeah.
conversion that we have to go through to make sure the answer is
What are
correct?
what are the units of Rydberg's constant?
I don't know.
Yeah, joules.
So I heard somebody say it.
Just multiply times the third. Since you multiply.
10 to the 10 to the third, right? So 1,000. So yes, you do need to convert, because remember that when we're doing this math, yes, we're canceling out numbers, but we're also canceling out units. So if we have our constant with units of joules, can we correctly cancel out if the units given are kilojoules?
Oh no.
No, right? So we need to convert into joules so we can cancel out all of
Oh,
our
okay.
units.
Thank you so much.
Yes. So does anybody have any other questions?
Isn't in some cases they ask for like kilojoules at the end, anyways?
Yeah, but then you'd have to convert
Sometimes.
back to kilojoules.
Yeah,
Because
yeah.
if you try to keep it in kilojoules, you're not going to get the right answer.
Any other questions?
Is it possible you can show us a problem like that? Like on the workbook? I don't know if you have it in front of you, like
Okay.
5 on
Question 5. Okay. Question 5. The energy required to ionize 1 mole of lithium atoms in the gas phase is about 520 kilojoules per mole. What frequency should 1 mole of photons have in order to ionize 1 mole of lithium gas atoms? So in the question, what are they giving you?
520 kilojoules per mole.
They're giving you the energy, right? So it'll be 520 kilojoules per mole. And what are you trying to find?
The energy required to ionize 1 mole.
Well, that's what they give us. That's what the E is. So what are they asking us to
Frequency.
find?
Oh yeah,
The frequency, right?
Yeah, the
So,
frequency.
so what equation are you going to use?
You would use the E equals. Wait, no, never mind. You use the frequency equals energy over Planck's constant.
Frequency equals energy over Planck's constant. Well, yeah, that's another way of looking at it, right? But the original equation is Planck's constant, Planck's equation, right? So E is equal to H times V, right? But again, if you're trying to solve for frequency, you would just move the Planck's constant to the other side, right? So you have energy in kilojoules, and Planck's constant in what units is it?
Joules per mole.
Joules per mole. So what are you going to do? How are you going to start this equation? This problem, I'm sorry.
Wait,
So
before
you
we
just-
keep going, I don't agree with the units for Planck's constant. What are the units for Planck's constant?
Joules times seconds.
Exactly. Sorry, keep going.
So it's joules per seconds, right? Okay, so what are you going to do to solve this problem? So what is the first step that you're going to take?
You convert the kilojoules to joules.
Convert the kilojoules to joules, right? So right now you have 520 kilojoules. So kilojoules, what are you going to do to it to convert it to joules?
You multiply it times to the third. Well, yeah.
You multiply it times 1,000, right? Because in every 1 kilojoule, you're going to have 1,000 joules. So you multiply 520 times 1,000, which should give you 520,000, right? So your new number for energy is going to be 520,000 joules per mole, right? So now, what are you going to do? What's the next step you have to take?
on the atoms, I guess.
I'm sorry.
The atoms.
What about
Isn't-
that?
Don't you like divide times isn't it Avogadro's? No?
Okay, so the problem is asking you to find the frequency or what frequency should 1 mole of photons have in order to ionize 1 mole of lithium gas atoms. So does it make sense that you have to convert to moles? Or do you have to like eliminate the moles?
So it's asking us to work with moles. Do we already have moles?
Yeah.
So does it make sense to convert out of moles?
I mean, asking for an atom, so I was like, oh, then.
But it
it's,
says 1 mole. It is telling you atoms, but it's 1 mole of atoms. So do you need to convert out of moles?
No, I don't think so.
No, right? You just stick to your guns. Be confident. We stand confident students.
yeah, so you wouldn't have to convert to moles, right? You wouldn't have to change, or you wouldn't have to use Avogadro's number by any means, right? So if you already have all that you need, what are you gonna do?
Plug it in the formula.
Plug it in the formula, right? So energy, it's equal to 520,000, right? Joules per mole. What about H? What does Planck's constant equal to?
The 2.18.
6.63 times 10 to the negative
6.63 times 10 to the negative 34, right? Joules per what? Or joules
10
times
seconds.
10 seconds, right? Okay, so if you plug this into your calculator with parentheses, what should you get?
By the way, it's not a bad idea to be plugging it into your calculator just so you have that practice for the exam.
7.84 times 10 to the
Times 10 to the what? I'm sorry?
38.
Times 10 to the 38, right? So 7.84 times 10 to the 38. What about units?
One per second or hertz.
1 per second or hertz? Okay, exactly. So are we missing something? Look at the units here.
Would it be over moles?
It'll be over moles. I don't know. Would it? Would it not? As Sophia said, we need confidence. Be confident on your answers. Because
We stand confident students.
the teacher could very easily, well, not the teacher, right? The professor, the doctor could very easily tell you that, are you sure your answer is right? Or like look at you differently and you make it second guess your answer, it would still be right, right? So with confidence, what should the units be in this case?
Moles per second. Oh,
I'm sorry, could you repeat that? I'm sorry.
moles per second?
Moles per second? Let's go ahead and solve it mathematically, okay? So joules per mole over joules times second is the same thing divided by joules per second, right? If you do it by the reciprocal, it's the same thing as multiplying it by joules over second. Times. Well, no, okay, wait. Let's leave it like that. 1 over joules per second. So the joules are gonna cancel out, right? The moles, are they gonna cancel out?
So it's just moles per times second.
Times second, right? So we'll be hertz per mole. If I'm not mistaken.
I think it would be hertz over mole.
Hertz over mole?
Mhm.
Okay. So be hertz over mole.
Any second opinions, peer leaders? Third opinions, fourth opinions?
Answer like hertz times moles, and then another question that had the answer like hertz over moles. You get me?
Oh yeah, it should be hertz over moles since it would be 1 over mole seconds.
Yeah.
Look at you guys knowing stuff, taking down names.
Y'all are gonna put us out of a job. Oh, I'm sorry, was it Jasmine? What was your question?
I was just saying, like, in case they give us this kind of question and they'll give us an answer that says like hertz times moles, and then the other units like hertz over moles.
Well, what should be the correct answer according to our algebra?
It would be hertz over moles, but
Yeah, so then you pick the answer with hertz over moles, right?
Oh,
Oh my god, where's my mouse?
I think.
So does anybody have any other questions? I'm gonna take that as a no, okay? So I'm gonna go ahead and stop sharing my board. And yeah.
Awesome. Let me stop recording and then we'll do module 12. Yes?